These methods can help identify the effect of the molecular structure of electroactive organic molecules on charge carrier generation and dynamics, ionization potential, electron affinity, and band gap values.
These methods are a cheap and fast way to determine the most valuable parameters for many electroactive materials without the need to construct special devices.
The presented method can be used to analyze all types of electron-active compounds, such as those with delocalized pi electrons, including small molecules and large polymeric chains.
To begin the CV procedure, fill a clean electrochemical cell with 1.5 milliliters of electrolyte solution and cap the cell with polytetrafluoroethylene electrode holder. Insert working auxiliary and reference electrodes into the cap, with the working and reference electrodes as close together as possible without touching. Ensure that the electrodes are immersed in the electrolyte. Then connect the electrodes to a potentiostat, being careful not to let the connectors touch each other. For a reduction analysis, bubble inert gas through the solution for at least 5 minutes to remove dissolved oxygen. Then, raise the inert gas line above the solution and leave the gas flowing throughout the experiment. Once the electrochemical cell is ready, open the potentiostat software and select the CV procedure. Set the start potential to 0 volts and set the upper and lower vertex potentials to 2 volts and 0 volts for oxidation analysis, or to 0 volts and negative 2.5 volts for reduction analysis. Set the stop potential to 0 volts and the number of stop crossings to 6 and the scan rate to 0.05 volts per second. Name the data file and acquire a voltammogram. Check that the electrodes are clean and dissolved oxygen has been removed if applicable. Then, add 10 microliters of a 1 millimolar ferrocene solution to the electrolyte and acquire a reference scan. After that, empty and clean the cell and the electrodes. Fill the cell with 1.5 milliliters of a 1 millimolar solution of the compound to be analyzed in the electrolyte. Reconnect the cell to the potentiostat and sparge the solution if necessary. Then, set the start potential to 0 volts, the upper and lower vertex potentials to 0.5 volts and 0 volts for oxidation, or 0 volts and negative 0.5 volts for reduction, the stop potential to 0 volts, and the number of stop crossings to 10, and the scan rate to 0.05 volts per second. Name the data file and acquire this initial voltammogram. Then, increase the upper vertex potential by 0.1 volt for an oxidation analysis, or decrease the lower vertex potential by 0.1 volt for a reduction analysis, and run the scan again. Repeat this process until the full peak of interest is observed. If successive scans have shifted potentials, clean the reference electrode. Let it soak in the electrolyte solution for 1 hour. And then repeat the measurement. After completing oxidation measurements, perform reduction measurements or vice versa. Then, set the start potential to 0 volts, the upper vertex to 1 volt, the lower vertex to negative 2.7 volts, and the stop potential to 0 volts. Run the scan and adjust the potential window as needed to ensure that the full peaks are visible. Repeat the process at different scan rates and in the presence of ferrocene. To begin the UV-Vis-Near IR procedure, fill a clean spectroelectrochemical cell with 0.5 milliliters of an electrolyte solution. Insert the working, auxiliary, and reference electrodes and place the assembled cell in the spectrometer. Connect the electrodes to the potentiostat and open the potentiostat and spectrometer software. Take absorbance measurements on each detector as a solvent blank. Then, disconnect, empty, and clean the cell. Refill it with either a 1 × 10⁻⁵ molar solution of a compound in the electrolyte or with the electrolyte alone if testing a material deposited on the working electrode.
It is very important to set up the spectroelectrochemical cell properly and in the way as similar as possible to the spectroelectrochemical cell used to record the blank spectrum. Only this will ensure the registration of good results.
Place the cell in the spectrometer and reconnect the electrodes to the potentiostat. Apply a neutral potential to the cell and acquire a starting spectrum. Increase the potential by 0.1 volt and wait about 10 seconds for the process to stabilize. Then, acquire another spectrum. Continue this process until the first change is observed in the spectrum, and then save that spectrum. Next, increase the potential by 0.05 volts. Wait for 10 seconds and acquire a spectrum. Repeat this process until the first or second oxidation potential determined from the CV measurement is reached. Then, de-dope the film by applying a neutral potential. At the end, compare the spectra of the film before oxidation and after de-doping. To begin the EPR spectroelectrochemistry procedure for polymeric materials deposited on a working electrode, fill the spectroelectrochemical cell with the electrolyte and place it in the EPR spectrometer. Set up the manganese standard and adjust the instrument parameters to cover only the third and fourth manganese lines. Acquire a background spectrum, check for contaminants, and then remove and clean the cell. Next, refill the cell with the electrolyte. Place the electrodes in the cell with the reference and working electrodes inside the auxiliary electrode wire spiral, being careful not to damage the polymeric layer on the working electrode. Position the working electrode close to the bottom of the cell and the reference electrode near the upper part of the active section of the working electrode. Connect the electrodes to a potentiostat and place the cell in the instrument.
It is critical to set up spectroelectrochemical cell properly and not destroy the film deposited on the working electrode surface. Incorrectly placing the working electrode makes it impossible to register any results.
Apply a neutral potential and acquire an initial spectrum. Then, increase the potential by 0.1 volt. Wait 10 seconds for the sample to equilibrate and acquire another spectrum. Repeat this process until the EPR signal appears. Then, increase the potential by 0.05 volts. Wait 10 seconds and acquire another spectrum. Continue this process until the first or second oxidation potential is reached. And then reverse the potential steps and return to the starting potential in the same way. Then apply the potential at which the EPR signal appeared. Enable the manganese reference and record a spectrum to obtain a measurement with the third and fourth spectral lines of manganese. The onset potentials of both reversible and irreversible processes can be estimated from calculations based on the intersection of lines tangent to the CV peaks with the background, adjusted for the reference material. UV-Vis near-IR spectroscopy of this polythiophene derivative showed the neutral polymer absorption band diminishing and new polaronic and bipolaric absorption bands forming during oxidative doping, with an isosbestic point at 604 nanometers. The new polaronic band from 550 to 950 nanometers was attributed to the radical cations of biethiophene and paraphenylene-vinylene. A new bipolaronic band was observed between 950 and 1700 nanometers. EPR spectroscopy during reduction of this S-tetrazine derivative showed a hyperfine splitting pattern that matched a simulation consistent with the interaction of an unpaired electron with the 4 nitrogen atoms of S-tetrazine. A single broad EPR signal is often observed from conjugated polymers, indicating significant delocalization of the radical ion generated by the redox process of interest.
While performing reduction analysis during this procedure, be sure to properly degas the solution before the measurement to avoid any interference from dissolved oxygen.
Following this procedure, the electron affinity, ionization potential, and band gap of the investigated material can be estimated from the data.
By using this procedure, you can determine the impact of chemical structure on the investigated properties for a group of materials.